This is Topic 10 in Unit 1, Measures of Relative Standing in Box Plots. So far for descriptive statistics, we've talked about measures of center, which was one number to describe the entire data set that was typically in the middle, as well as measures of variation, which described how spread out or scattered a data set was. Lastly, we have measures of relative standing. A measure of relative standing are values that show the location of data values relative to other known values in the data set. Previously, in Topic 9, we looked at the range rule of thumb as well as the empirical rule, which were two ways to talk about where a specific value lied in the entire data set. Measures of relative standing is similar to this, except for we're talking about where a single value is relative to other specific values. The major one that we're going to be talking about is a z-score. A z-score tells how far a value is away from the mean relative to the standard deviation of the data. It is found by subtracting the mean from the value and then dividing by the standard deviation, which we'll see in the formula a few bullets down. A z-score tells how many standard deviations a value is away from the mean. It is unitless, or sometimes you may see it described as standard deviation units. If a z-score is negative, then that value is below the mean, and if a z-score is positive, then that value is above the mean. Z-scores are always rounded to 2 decimal places. This is one of the more important rounding rules that we will have. A value is considered unusual if its z-score is greater than 2 or less than -2, and this is the same exact thing as the range rule of thumb. So this means that if it's more than 2 standard deviations away from the mean in either direction, that it's considered unusual. And then lastly, a formula version of the description is the z value, the z-score, is equal to whatever your x is, your individual value of focus, minus the mean divided by the standard deviation. So ultimately, what you want to remember is this one right here, that a z-score tells how many standard deviations a value is away from the mean. And if it's positive, it'll be above, and if it's negative, it will be below the mean. So example 1, IQ scores have a normal distribution with a mean of 100 and a standard deviation of 15. Find the z-score for an IQ of 128 and determine if this value is unusual. So I actually like to show these calculations by hand because a lot of times they don't look the same typed out as they would if a person was writing them themselves. So a z-score is what we're looking to find here. I prefer this version of the formula because it will work no matter what type of situation you're dealing with. And the individual value, the x, is just the value that you're interested in specifically. So in this case, 128 is our value that we're looking at comparing to the data set. So when you enter this into your calculator, you need to make sure that you either use parentheses around your numerator or you do this in 2 separate steps. I would probably do 2 separate steps personally. So 128 minus 100. Let's get this calculator going. This calculator isn't always going to work, but I would hit the enter button, which is what you do no matter what kind of calculator you'd have, and then divide this number by 15. So what this tells us is that an IQ of 128 is 1.87 standard deviations above the mean of 100. So this doesn't have the original unit as the original data, but you can interpret it as standard deviation units. Whatever the standard deviation is in, it will be the same one technically. So this is not unusual because it's in between -2 and 2. So this is the range rule of thumb again, but except for instead of having the standard deviation given to you, you'll be working with it using the z-score. So 1.87 is within normal range because we're close enough to the center of 0 which would be the z-score for the mean of 100, that we don't call it unusual. So the second example shows a little bit wider of why z-scores are pretty useful. So this goes back to the Oscar winners. As of 2006, Oscar winners for the Best Actress had a mean age of 35.8 years and a standard deviation of 11.3 years. Oscar winners for Best Actor had a mean age of 43.8 years and a standard deviation of 8.9 years. Which age is better or more unusual relative to their gender? So we're trying to see how far away from the norm is more unusual. A woman with an age of 22 winning the Best Actress, or a man of age 57. So right now, these are definitely the age-old apples to oranges, because the women have a mean of 35.8 and a standard deviation of 11.3. The men have a mean of 43.8 and a standard deviation of 8.9. So it's the same kind of situation where we can't compare these two numbers directly because we don't have the same denominator. We don't have the same mean and standard deviation. So what we would do in this case is find the z-score for both. And it's important to notice the language here is more unusual relative to their gender. So this can be unusual in the higher direction, meaning they're older than we would typically expect. Or it could be unusual in the lower direction, meaning they were younger than what we would expect. So when you find the z-score for the woman of age 22, you end up with a z-score of negative 1.22. So it's important that your value comes first that you're interested in, and then you subtract the mean from that so that we end up with a negative because 22 is less than 35.8. So 11.3 is our standard deviation. That's going to be on the bottom. For the man, 57 minus 43.8 divided by 8.9 gives us a z-score of 1.48. So when the question asks which is more unusual relative to their gender, the male is actually farther away from their norm. So their norm is 43.8. The female's norm is 35.8. So to compare these, we have to take the whole picture into account. So another one that we're actually going to talk about more later on are percentiles. These are measures of location denoted P1, P2, all the way up to P99 and P100. They divide a set of data into 100 groups, and then there's about 1% in each group. Now the reason there's about 1% in each group is that unless there is a perfect multiple of 100 for your data set, you don't have the ability to break up the data evenly enough so that you have exactly 1% in each group. So sometimes there's a little bit more, sometimes there is some estimating involved. So here's an example for a percentile and how to interpret it. So if you scored in the 64th percentile on an exam, or maybe the ACT, that means that 64% of the people scored less than you. So a higher percentile means that you did better, granted that a higher number is better. Quartiles are basically a different variation of percentiles, and they are measures of location denoted Q1, Q2, Q3, and Q4. And they divide a data set into 25 groups, each with about 25%. So if you had 100 numbers, you could break up your data set into 4 equal pieces with 25 each. However, if you had 66 numbers, you can't break up your data set evenly. So I honestly don't usually do any of these by hand because there's so many different cases that you could look at. So the important thing is understanding this interpretation here. So the first quartile separates the bottom 25% with the upper 75%. The second quartile is the same exact as the median, and it separates the data set dead in half. The third quartile separates the bottom 75% from the upper 25%. We're going to be using quartiles a decent amount as we go on. And again, they're just a specific case of percentiles. So P25 is the same thing as Q1. Q4, the fourth quartile, is actually your maximum number. So that one isn't too much. So the interquartile range, the IQR, is the third quartile minus the first quartile. This actually kind of seems originally like it is not something that is very useful, but it really describes where the chunk of your data is. We also use IQR in outliers description. So an outlier is a value that is less than Q1 minus 1.5 times the IQR, which is kind of seems like a mouthful, but it's not too bad when we look at an example. Or if it's greater than the third quartile plus 1.5 times the IQR. So it bears a lot of similarities to the range rule of thumb, but it also is slightly different in that it's not using the mean and standard deviation. It's using quartiles instead. So another descriptor we have is the 5-number summary. And these use the quartiles. And this is why when we mentioned box plots in topic 5, the statistical graphs, we mentioned that we couldn't do them yet. And this is because they use quartiles to design their graph. So the 5-number summary are these 5 numbers in order. If you switch them and put the max on top and the min on the bottom, as long as all these are switched as well, that's okay too. But I usually write the numbers low to high. So it's the minimum value, quartile 1, the median, which is the same as quartile 2, quartile 3, and then the maximum value. So finally, we get to create a box plot on our own. For now, we're going to be creating the box plots by hand, but in a future video, we're going to see how to make all of the graphs that we've talked about in SPSS. A box plot is also called a box and whisker plot, which is what you might know from another class. It's a graph that has a line extending from the minimum to the maximum with a box drawn around the first quartile, the median, and the third quartile. So we'll look at an example of that. These are the steps that I'm going to cover when I discuss the first box plot that we're going to make. So this is here for you if you want to use this in the future as we're going make more box plots, or now if you want to follow along. Okay. So use the given sorted values. They are the number of points scored in the Super Bowl for the winner for a recent period of 23 years. So all of these are the scores for the winners in the Super Bowl. And from that, we want to create the 5-number summary, which we're going to do in Stata. Create a box plots, which we will do for now by hand. And determine if there are any outliers, which we will use with the 5-number summary values. So let's get Stata open. I did clear my data editor. So you can either clear it if you were working on it previously, or you can open a new session. So let's call this score of winners. It usually doesn't matter what you name this. And so again, you want to select the fill with missing data. And so now we want to go through and enter in the scores of our winners. So I double checked my data, and this is the last time that I will show the data entry. So The 5-number summary we're going to get from the original descriptive statistics menu that we were using. So this is describe data and then summary statistics. And you have to check this second bullet now. So display additional statistics. You have to select that one in order to get the quartile information. So when you hit OK, the output window is going to have all the information. And so we need the 5-number summary from this. And I would call this 41. Oops, we need our minimum first. So the smallest number that happens are going to be displayed along the side. And this is going to take into account that issue where if you don't have a perfect multiple of 100, you aren't going to be able to get, or 50 for quartiles, you won't be able to get the exact numbers. You're going to have an estimate for the percentiles and quartiles. So the first quartile is 41. The median, 54. The third quartile is 61. And the maximum is 75 here. So these 5 numbers in order are the 5-number summary. Some people like to label them. I think it is best to label whatever you can, but this is assumed. If you say 5-number summary with these 5 numbers, they're assumed to be the minimum, maximum, and the quartiles. So to create a box plot of this by hand, I would put a number line along the bottom. So my minimum was 36 and the maximum was 75. So this is not done on a grid or anything. This is just to kind of roughly construct this box plot. The minimum and maximum are where I would start and put a line straight up and down at those. And then the quartile, the second quartile and the third quartile are lines up as well. The 3 lines in the middle are going to create 2 rectangles that touch each other, and then a line will extend from the middle of those to the min and the maximum. So what you have to remember is that these, of the data set, this is 25% of the numbers approximately. This is 25%, this is 25%, and this is 25%. So what you would want to think about when you look at this is that a lot of the numbers, okay, are in between these 2 values here, 54 and 61. So it's the same amount of numbers that happen here. So there's a lot of scores that have these values in common. Whereas on the other hand, a score of 75 is pretty high in football. So this quarter to the right, that is still the same amount of numbers here, but it just is a lot more spread out on the number line. So if we were to find the standard deviation of each of these pieces, this one would be pretty big in comparison to this one here. So interpreting a quartile, a box plot depends on thinking about that each of these is 25%. So lastly, determine if there are any outliers. So again, the outliers depend on the quartiles. So here we have Q1 minus 1.5 times the IQR. That's going to be the cutoff for our lower determination. The right-hand side has a cutoff of the third quartile plus 1.5 times the IQR. So think about this according to the box plot. We say, hey, okay, 50% of the numbers are surrounding the center from the 41 to 61 here. So we're kind of using that as the amount of distance that we're willing to allow to be normal, let's say. And then we give that distance 1.5 its length. So 41, our first quartile, minus 1.5 times that distance is 11. And there are no scores that are less than 11. So the lowest score that we have recorded is a 36. On the other hand, Q3 is 61 plus 1.5 times this IQR is 91. And there's no scores that are above that. So for this example, there are no outliers. Just again, remember that the IQR is the Q3 minus Q1, and that is going to give us a distance of 20 here. This topic is pretty short, especially in comparison to the previous topic. So definitely make sure that you go through all of these examples again. There will be more that will be posted before the exam, but for now, all of our box plots will be made by hand, and the 5-number summary is an output from Stata. Please feel free to email me if you have any questions.